Hello, Calculus 3. It is Calculus 3. And you can tell what we're going to do. We're going to do parameterized by arc length. Well, that was in the title of the video and in the subject line, so it's no big surprise. And it's a wimpy one, but it's a nice one. It's it's a helix. This time t is along the x-axis. So the helix would be circling around in the zy plane, dragged along the x-axis. So it's a spring laying on its side. That's what the curve is. Now, I did for you the calculation for the arc length, and I want to emphasize more carefully than I did in class the place that u occupies. U is a dummy variable. This little letter u, it was all t's, but I need a t right there. There could be times when you would apply the fundamental theorem of integral calculus to this integral. You take the derivative with respect to t, and it would not do in that case to have a t here and a t here and throughout. Very confusing. Not good math penmanship. So what the math people do is, when this letter doesn't matter, because it's going to be taken over by that letter, you let it be a dummy letter like u. So this letter u, it's a variable, but it's going to go away when I do the integral. So all I did here was the length of r prime. You know what I mean. I've got the length of r prime formula inside of the square root. It's the arc length formula, and we all know that cosine squared plus sine squared is 1. So we just get a square root of 2 u evaluated from 0 to t. So it comes out to be square root of 2t. So that allows me to write this important little animal over here. T equals s over square root of 2. Then, if you can get t equals, you get to put that quantity, in this case s over square root of 2, in those 3 parking places. See, all those t's get replaced with s over square root of 2. This is the same curve. It's the same set of points as that. It's literally the same little spiral running along the x-axis. It's the same spring, but the points occur, in a sense, at a different speed than the original. If you think of t as a parameter, this one, the t is being replaced with s over square root of 2, so in a sense, the particle traveling this spring is going a little slower. If you want to think like that, it doesn't really matter. The main thing is this s over square root of 2 is a superior variable. It's sort of a variable that has been built to go with this curve. We've parameterized by arc length, and it means a lot. We have now changed the parameter to something that has been built to fit that curve. We have hot rodded this curve. We have set this curve up to be very nice. And the 2 famous properties of a parameterized by arc length curve is the unit tangent is just r prime. You don't have to do any other hooky dookie with it. The length of r prime is guaranteed to be 1. And then the other one is you can get the arc length from the base point by just saying, well, how far are we going? If we go from 0 to 3 pi, the answer is 3 pi. No work. So let me scroll down a little bit for you, and we'll see the work that we do to verify these 2 properties. I've got it all on one screen for you. How great is this? So here's my r prime. The length of r prime is done out, and a nice thing happens, because 1 over square root of 2 is, because this is r prime, 1 over square root of 2, that's the first coordinate squared, becomes a half. This thing becomes a half cosine squared of s over square root of 2. So that thing is going to become a 1/2 because I square it. Same thing over here. This minus sign doesn't matter at all. This becomes a 1/2. So I have 1/2 cosine squared plus 1/2 sine squared. That adds up to 1/2. So this 1/2 plus this 1/2 is equal to 1. So I told you it would happen, and there it is. And now the main payoff. And I didn't emphasize this enough in class. That's one of the reasons why I'm doing it in this video. Here's the big payoff. And this is what happens every time you have parameterized by arc length. Check it out. Here's the arc length formula for this curve. I picked from 0 to 3 pi. It could have been from 0 to anything. It doesn't matter, because here's the only place where that 3 pi occurs, right there. upper limit of integration. That's the structure for this arc length integral. Remember, the arc length integral is the sum of the squares of the first derivatives of the coordinate functions, which is this. It's this thing over again. It just goes right in there. Well, I know how this goes. That's a 1. This whole thing is a 1. And that's why this second valuable property always happens, because what's the integral of 1 ds? It's an s. Evaluate from 0 to 3 pi. It's 3 pi minus 0. My answer is 3 pi. How great is that? That happens every time. That's why this little move right here, this piece is built to become 1. And when you do arc length integrals, this square root no longer bothers your mind. You paid for it one time for all. So that's why that always turns out like that. How cool is that, huh? So that's why the fuss over parameterized by arc length. 2 very valuable time-saving properties come from that. And I like asking questions about this. I'm partial to it. I've lived through parameterized by arc length. I've seen the value. You might go your whole life without ever saying the phrase parameterized by arc length. I parameterized. Just a second. I gotta fix that. There we go. Parameterized by arc length. Ha! All right, so it's all fixed up. And if you watched the video, thank you. I appreciate that. You should be able to at least partake in these kinds of properties, be able to use these properties so that you don't have to do this long calculation. I don't want you to do these long calculations. So if I ask you, if I give you a curve that's parameterized by arc length and ask you to find the length of r prime, just tell me one. I don't want. If I want you to do the steps, I'll tell you to do the steps. But I want you to take advantage of this shortcut and to know these things. Same thing with finding the arc length. If I ask you to find the arc length from 0 to 8 pi of r of s, the original functions, the original functions up here, find the arc length of that from 0 to 8 pi. The answer is 8 pi. You don't have to do the work. That's how it goes. So I'd love to be able to ask some questions like that on a test where, wow, you know your stuff and you didn't spend time on it, even if it's a take-home test. I don't want it to be I don't want you to do it the long way unless I tell you to do it the long way. Okay? All right, you guys, another short video brought to you by Calc 3, MS 231. See you later.